That's this number. This is Planck's constant. That's my h. Here's my speed of light. When I multiply these together and divide, I get 3.16 times 10 to the minus 19th joules. Okay, so this is my energy. Now, what is that energy of? This is the energy of one photon of that light. It's one photon. Okay, now, do we have one photon in that wave? No, there's lots and lots and lots and lots of photons. All right, so this would be the amount of energy in that red light of one photon. I'm going to give you we're going to use this example. Let's label this like an A, and then we'll do B. Calculate the energy in kilojoules of a mole of these photons there's a couple things that I want to remind you of. How many particles are in a mole? Because we do need to know that. And that's Avogadro's number. So for those of you that don't remember, 1 mole of a substance is equal to 6.022 times 10 to the 23rd particles. So we have, here's the number of joules per photon. It's in joules. We got to convert it to kilojoules. And then we don't want to know one particle. We want to know for a mole of particles. So this is actually pretty easy. So our energy is we're starting with 3.16 times 10 to the negative 19th joules. I want to convert that to kilojoules. So we have 1,000 joules in 1 kilojoule. So that means my joules will cross out. But then I need to know how many exact particles that is. 6.022 times 10 to the 23rd photons in 1 mole. And we multiply across, and it turns out that 1.90 times 10 to the second kilojoules per mole. Okay, that's how much energy you would have in kilojoules per mole of photons. Typical problem. Okay, this is just a typical problem where you might figuring out how much energy is in that photon. Let's do a couple more problems and we'll call it a day. Okay, so I'm going to put the equation, I'm going to put the problem down, and then I'd like you to try it and then come back and check. Okay, so calculate the energy in joules of a yellow light that has a wavelength of 567.3 nanometers. So go ahead and pause it. Pause it, do the problem, and then come back and I'll go through it with you. So I'll go ahead and pause it. All right. Hopefully you've done it. So let's go ahead and go through it. So it's going to give us our wavelength. And again, it's in nanometers, so that's going to be a problem. Okay, we need to get it into meters. I'm going to do that first. So my wavelength is equal to 567.3 nanometers. I'm going to convert it 10 to the 9th nanometers per 1 meter. So I have 5.673 times 10 to the 7th meters. Okay, so I want to know the energy in joules, okay, and that's of 1 photon. So now I can use E equals Planck's constant times the speed of light over wavelength. .626 times 10 to the minus 34th joule seconds times 3.00 times 10 to the 8th meters per second, all over 5.673 times 10 to the 7th meters. And I end up with 3.50 times 10 to the minus 19th joules. And again, that would be the energy in 1 photon of that light. All right, let's try one more problem. It's a little bit different. Let's calculate the energy in joules. Of a radio wave that has a frequency of 99.1 megahertz. So this is giving me a frequency this time, and I want to calculate the energy. Now, problem is going to be this megahertz thing. Okay? And hopefully you can make that conversion. You should be able to do that. It's just metrics. Okay? So 1 megahertz is equal to 1,000,000 hertz. Okay, you should know that. Okay, you should know that. So we want to get this into, we need this number in just hertz or per second. So we can use this conversion. So our frequency is 99.1 megahertz. For every 1 megahertz, we have 1,000,000. Let's just use 10 to the 6th hertz. So we end up with 9.91 times 10 to the 7th hertz. Remember, you could write this as 9.91 times 10 to the 7th waves per second. So it's just -1. Both are fine. Okay, both are fine. So now we have our frequency. Now we can actually just put it into our energy equation. Energy equals Planck's constant times frequency. Well, we know what Planck's constant is. Times our frequency. To the 7th. When we do that math, we get 6.57 times 10 to the minus 26th joules. And again, this is the energy in 1 photon. All right, so really what you need to be able to do is you need to be able to calculate energies of those photons. You need to be able to go wavelength to frequency and frequency to wavelength. All right, so you should be able to do all that. There are some conversion things in there you need to know too. All right, so that's where we're going to stop today. And on Friday, or next class, next lecture, we'll be dealing with how this applies or where this light is coming from when we're talking about the atom, okay? And this has to do with what we're doing in lab also. All right, so make sure you're doing the work, and we will talk to you soon.